That's definitely true. All right. Beth and Lindsay. Let's
Okay.
do it.
Seriously, not gonna let me present. That's fine. All right, so back to smelling things. We have Seychellene, and it is a sesquiterpene, like Scott was mentioning. So they usually have the formula C15H24, and it is a component in patchouli oil, which is a common essential oil and perfume scent. So this is just like a gas chromatography report of patchouli oil, like what they have in it. And then there's Seychellene, and it is responsible just for the aroma, so I bet it smells pretty good. And it's also an antiseptic, so that's interesting. And it shares its name with Seychelles, which is an archipelago off Africa's east coast. So if you Google Seychellene, one thing will come up for the compound, and every other thing would be about traveling. So that was this is the first scheme that I'm going to talk about. It's by Fukamiya, and it was published in 1971. So it has this really interesting yellow box that we'll get to. The first step is an alkylation, which is pretty interesting. So usually I'm used to seeing like sodium amide in the context of like alkyne alkylation. That's like kind of the only way I've seen it before. But in this case, that NH2 is used to deprotonate this top methyl group, so this one right here, which leads to this intermediate through residence. So since if you take off this hydrogen right here, you have a negative charge on this top carbon. Those electrons move down to form an alkene on this exterior portion, pushing these electrons to form a carbanion down here. So that's this intermediate. And then it's basically just an SN2 reaction between the carbanion and this alkyl halide. And it's a bit hard to tell, but this is also an iodine. So that just didn't really look quite normal, but there's two iodines. That's why there's one still remaining over here. And then the new bond is just formed between this carbon, and the iodine is removed.
That's very clever.
Hold on, there we go. And so the next step is something we've also seen before, bromination with NBS and bromosuccinimide. And so I showed down here the allylic position. So there's two places this bromine could have added, but it went here because the alkene is more substituted. So that's just, when we learned about this in Orgo 1, the steps were to find those allylic positions, and then you can add the bromine to wherever they are. So this is just a gentle source of those bromine radicals, and it adds to this carbon on the end. The next step is also kind of interesting. It's a reduction of an alkyl halide using this chromium chloride. And so this is what I think happens here, because it was mentioned briefly that chromium chloride can be used to reduce alkyl halides, but I believe it kind of coordinates with that carbon to leave this negative charge. And then those electrons that were negative can now move into a double bond, forcing these electrons that were previously here over there. And then I believe the bromine, since it's now an anion, will be able to deprotonate that position to allow for the double bond to be formed in a new area. So
it's very strange.
It is really weird. But I think since chromium is one of those active metals, it's listed in the etc. category, it can coordinate with the carbon and then subsequently break off, leaving it as a free metal and the bromide ion to be able to deprotonate this position to allow those double bonds to switch. And now they just keep moving around these double bonds. So the fourth step is an isomerization using toluene sulfonic acid. So it basically just like deprotonates right here and then allows these to switch to, like makes an enolate, and it allows these to kind of maneuver around in the ring to form a more stable conformation. So if you look at where the double bonds are in this structure versus where they are here, it is better for the double bonds to be like contained within the ring because they're more substituted than they are to be like extraneous, like out on the side. So this just isomerizes it into a more stable conformation for the remainder of the synthesis.
And they're conjugated now to the ketone.
Yep. And then they add this amine group down here. So this dimethylamine, which is going to be used in the next step. So they just kind of substitute that out for the iodine using ethanol. So
you know what kind of reaction that is?
Is that also, no. Is that also an SN2?
It is, yep. Yeah.
So there's another SN2 reaction. And then this is where it gets kind of interesting. So usually for a cope elimination, the first step is actually using MCPBA. However, they discovered that I guess hydrogen peroxide works just as well to form this kind of initial weird compound right there with the negative oxygen, the positive nitrogen.
It's called an N oxide or an amine oxide.
Oh,
yeah.
Okay.
Yeah.
And then, so this next step where Scott wrote buckle up is called a cope elimination, and they heat it really, 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 really hot, so 430 degrees Celsius. And then the one afterwards is a Diels-Alder. So here is an example of the cope elimination. So like I said, the first step in order to make this N oxide is usually MCPBA, but they use hydrogen peroxide. And it's a syn-periplanar leaving group. So it and the hydrogen have to be syn and in the same plane. So that's why they showed this Newman projection here. And I'm sorry, like, I don't know why, but
Did you make that ChemDraw figure?
This one down at the bottom?
No, the one up top.
No. The blurry one down at the bottom is me.
Oh, okay.
I don't
Well,
know
they're
why
both very nice.
Okay, thank you. I don't know why, but when I post ChemDraw things in there, it makes them blurry. But this is essentially what happens. So it's 6 electrons moving. So the oxygen, which is negative, attacks and takes this hydrogen off to the side, that's syn-periplanar beta hydrogen. And then its electrons move to form that double bond to make the alkene. And then the nitrogen breaks itself away from the carbon of the alkene. And that's how you get this like dimethyl nitrogen alcohol thing over here. And that's forming the alkene. So I drew it down here, but I apologize, it's a little blurry. So in this case, it's the same thing that's happening, that oxygen is able to take the hydrogen, those electrons move to form the double bond, and then the nitrogen group just breaks off, and so you get this as a byproduct. And now you have a new alkene off to the side. And then they use this alkene to do an intermolecular Diels-Alder, which is really, really tricky to see. So I circled where the double bond forms on the starting compound to where it is in the final compound. So I have this just down here as like a reminder of what the Diels-Alder does. So here's your dienophile and here's your diene. And this carbon form a bond here. This will move there. These and will move out and form a bond there, which is why this forces this group with the ketone up as a bridge. So if you think of it, it kind of approaches from the bottom. That's why it forces this ketone group up and over to form that bridge. And then you have this methyl group sticking off the end is this one. This one, I believe, is here. And then this one on the end is the thicker line off to the side. So it's a little hard. Cool. It's a little hard to keep track of, but it's a Diels-Alder that kind of forms under the bottom, causing that bridged structure for the remainder. And then from there, this is like the end. So they use hydrogenation just to remove that double bond that they formed with the Diels-Alder. And then like in Nye and Emily's, they have methylithium, which will take this ketone and transform it into a tertiary alcohol. And then they use thionyl chloride and pyridine to just dehydrate it down to an alkene. And that's Seychellene.
Nice.
Lindsay, do you want to share it on your computer, or do you want me to just like, okay.
Yeah, I'll share it.
Cool. Let me see if I can, there we go.
This is nice chemistry.
Is there a lot of background noise?
No.
Are you in a different area of your house?
I'm at my dad's apartment in Pennsylvania.
Oh.
And so I just like don't know where anything is. I don't know how to turn. I can't reach the fan to turn it down. It's just kind of, there's no kitchen table. I don't know where to sit. That's why I've been moving around. Like there's nowhere for me to sit besides the couch. It's very uncomfortable. Sorry. I don't know how to make it present. Sorry, this is just going to be a minute, I think.
I think it's under view. Yeah.
Cool.
All right.
Okay, so I did like kind of the second part, the second scheme of, I can't say it, I'm not even gonna try to say it. And so the first step is acylation, and lithium dipropylamide right here acts as a base and basically deprotonates this right here, and then it forms an oxyanion, and then the MESiCl2 basically adds onto it, and the chlorine leaves as a leaving group.
Yes.
And then we have a Diels alder, which the diene is right here. That's the two, this kind right here, you can see the shape of it. And then this is the dienophile. So it actually, you can kind of see in the products that these methyl groups, it ends up being back, like pointed towards the back. And then the front of the molecule is like right here in this, in the product. So you can kind of see that the bond was formed between like these two carbons and this carbon, these two carbons right here.
And the water removes that trimethylsilyl group, so it uncovers.
It like deprotects it because it's used. It can be used as a protecting group.
Yeah, it's kind of crazy because the trimethylsilyl group, that red double bond that makes it into a diene, it kind of traps that enolate as the double bond so that you can use it in a Diels-Alder reaction, and then they take it off to remove the ketone.
Yeah.
That's very that's very clever, I think.
It is very clever. Yeah. And then the
it's
next
something DJ would do.
It is something DJ would do. Is an oxidative decarboxylation. We don't really know exactly how it works. But all we know that the PBOAC4 is a selective oxidative agent. And then in step one, you basically just heat it with a bunch of water, and we think it forms like 2 carboxylic acids, like right here. And then the PBOAC basically removes those carboxylic acids and turns it into 2 CO2s. So then it's like turning just basically the group into CO2 as like leaving groups. And
25%, that must have hurt. You know what I mean?
Yeah.
Yeah.
Definitely.
Yeah. What journal was this in? Can you just show me real quick? Yeah, tetrahedron letters.
Yeah, not very good.
That's why they got dinged. I think it's right there. Okay.
Yeah. Okay, and then we have a little, am I on the right step? Alkylation. And basically what happens is it starts with a base to form, I think it forms an enolate.
It does form an enolate.
Yeah, it forms an enolate, and then the enolate attacks this bromine right here, and then the bromine leaves as a leaving group to form the bond between this carbon and this carbon right here, which is this bond right here.
Nice.
And then we have a nice radical cyclization. And what happens is the tin-butyl tin hydride is a way to just generate radicals. And so what we think what happens is that it takes it takes an electron it leaves an electron from the bromine and takes an electron from a bromine. So then you have this radical on this carbon right here. And then a radical reaction happens between this carbon and 1 electron from the pi bond, and it forms this bond right here. And then the tin-butyl tin hydride, then you have another radical left on this carbon, and it forms a bond between a hydrogen on the tin-butyl tributyl tin hydride and then puts a hydrogen on it. Does that make sense?
Radical chemistry is tough.
Very hard to explain with words.
Yeah.
And then the next steps are just reductions. So we know that this is just getting rid of the double.
Oh, wait. I think you have to show the previous molecule again. Oh, yeah. See previous molecule, there's an alkene at that red position.
We can just go back to here. Okay.
Oh, okay. There you go.
So it gets rid of this double bond right here, and we know it's just a syn addition with H2 and palladium carbon. And then the next step is with methyl lithium and ether. And it's sort of like a Grignard, like they could have used a Grignard in place of this, but they just chose to use methyl lithium. And methyl lithium acts as a nucleophilic Grignard reagent, and then it's the CH3 minus of the methyl adding to this carbonyl carbon. And then this is just protonated with acid during the workup. And then we just have a dehydration with the Sokal-2 to get rid of the water to form this double bond.
I appreciate it that you call it Sokal-2 because that's what I call it in class, but it's important now that you're an alumnus of the class, if not yet the college, that you also know that like in the rest of the world, people call that thionyl chloride. What?
I just think it's funny. I have to write that down because I'm not going to remember.
Yeah. The other one that people do is sometimes people use potassium T-butoxide or KO-TBU, right? So people call it Cody-boo, but like you shouldn't do that around, like there's only certain places where it's okay to say that, and you just want to know what it really is so you don't call it that in the wrong place. Do you understand what I'm saying?
Yeah.
So like if you're giving like a scientific talk at a conference, you want to call it potassium T-butoxide, but if you're like just talking to your friend, you can call it Cody-boo. You know?
Yeah.
All right. So same thing with this. Sokal, fine with us, but thionyl chloride to the rest of the world.
Okay. I just noticed that it says very largely one isomer as their explanation for like.
Yeah, I just sort of ignored that. Yeah.
Very largely. Oh yeah. So yeah, that's a little weird that they didn't actually give a number.
Or a base.
Yeah. I can see how it would prefer to add to the face with the alkene because it's ever so slightly more accessible, right? Because that alkene is flat, whereas on the other side, you have those sp3 carbon-hydrogen bonds. Do you see what I'm saying?
Yeah.
Yeah. Nice.
Yes.
All right. Thanks, Lindsay and Beth. Emily and Naya, do you have any questions for them? Kind of similar chemistry, actually, in both of them. Great. Okay. So what you all should do is, have you been able to meet at all to talk about the group project as yet?
We are today.
Oh, are you? Okay. So tomorrow what I can do is just talk a little bit about, well, what I was planning on doing was talking a little bit about some like techniques people use to manipulate DNA to make things that are useful, particularly with respect to like if you want to make a certain protein or enzyme, how do you do that, right? Like how do you get the gene that encodes for a protein that you might want to make and then move that gene around so you can get like bacteria, for example, to like make that protein for you so you can use it. So like people in the lab do that like all the time. And sometimes we have to make new ones. So it's sort of nice to like see that sequence of events. So you know like where that stuff comes from and how people I guess do that. And then I think in all of your cases, right, like there have been proteins that people study like in purified form. And this is generally how people get purified protein is they get the gene that encodes for that protein and then they put that gene in the simplest organism they can, typically a bacteria, and then they get the bacteria to make the protein, and then they purify it from the bacteria, even if the gene is like a human gene or a gene from a non-bacteria. So so some of it might be like a little bit familiar to you, like the PCR reaction. Emily talked about that some, but I'll just talk about it in sort of a slightly different and actually simpler context, because I think Emily was talking about that mostly with respect to making like mutations. So and then the next big thing for you all to do would just be like the group thing, which I'm a little bit leaning towards maybe having you do that on Thursday, and then on Wednesday we could just like have like we could just chat about how things are going and if you have questions, and then also on Wednesday maybe we could also talk a little bit about like we could start talking about like stuff that the college wants you to do for the summer scholars thing too.
Yeah, we just got an email from them about the thing next week. We have to have like an elevator pitch for our project.
We can work on that a little bit. Yep. Yeah, so that just means like it's harder than you would think. It's sort of like just a few sentences like to talk about probably you would just want to talk about like the topic that you've been focused on, and and also to talk about it to somebody who's not a scientist, right? So like how would you explain it to your mom or your dad or like an aunt or an uncle or something, but only if like you're walking from like the car to like the stands at like a little league baseball game. You know what I mean? Like that's how much time you have.
It's like very specific.
That's very specific.
Yeah. It's that time of year, you know? Well, actually, Little League is probably off this year, but normally there would be like kids playing Little League. All right. Lindsay, that was out of control. Okay. Good. Well, I hope things go well for you all today. What time are you going to get together?
Like 1:30.
Okay. Okay. Anything else for me?